So integrating both sides, Vt becomes xt. And then right here, we would just take this exponential and we would divide this by, and we would divide it by it. And which would be left off xt equals to negative 50 over 0.0693 e to the power of negative 0.0693 t plus c. So now we just need to find the c. So this is a constant, and we will use position 0 to time 0, so x of 0 equals 0 to solve for c, and then we would just plug it in, c equals 0, and then t equals 0 right here, which would give us this, and e to the 0 is 1, so we would just take c to the negative side, to the left side, and then divide both by negative 1 in order to find the c. So the c we would get is 50 over 0.0693. And then we take this c and we plug it in into our equation, which since we were looking for c, we plug it into this equation, which would give us a full displacement equation of xt equals to negative 50, Okay, so next, as I was watching your lecture, to find the actual value, so we would have to take limit t to the infinity, and you were saying that as the time goes by, so that's how I thought of it. So as the time goes by to infinity, and so we would take this whole equation and then we'd put a limit t to the infinity, negative 50 over 0.693 e to the power of negative 0.693 t plus, this is our c, 50 over 0.0693. And then what I did, I just break them up. So I would have this side, it would be limit goes to the infinity for this side, and then also for this side the limit goes to infinity. What I did next is I just took out this, a negative 50 over 0.0693. I took it outside and I was just left with the limit t to infinity of e, negative 0.0693, and then we would have on this side limit to infinity of 50 over 0.693. And going on, limit of the constant, which is here in blue, limit of the constant equal to a constant. So this wouldn't change. So for this side, we will have this. And on the left-hand side, let me see, yeah, it just stayed the same. And then when you take, wait, I'm missing a t here. I'm sorry. Yeah, I'm missing a t here. Let me add it so it would make sense for a second. Yeah, so when you plug in infinity to right here to a t, and then you would have exponential to the power of negative infinity, it would just equal to 0. So when it equals to 0, we would have a negative 50 over 0.0693 times 0, which is 0, plus 50 over 0.0693. And then when you take it as a fraction, it gives us, I don't know, can you see the bottom? The distance is 721.5.
Yeah, see that. Right. Do you find out 0.0693 is annoying?
Yeah, I did.
I have a suggestion for you. Go to this line above p. You have p approximately equals 0.0693. You see you have p equals 1/10 ln half.
Yeah.
Just use this one. Simplify this.
Just keep it like that? Okay.
Yeah, simplify. What's ln half?
Ln half is it?
Right, the simplest version of it. It's ln 1 divided by ln 2, right?
Yeah.
It's ln 1 minus ln 2.
Minus, yeah, yeah.
Yeah, what's ln 1?
So negative ln.
Well, ln 1 is 0, right? So you have a 0 minus ln 2. So you get a negative ln 2. So ln half is a negative ln 2. A negative 1/10 times negative ln 2. So you have positive ln 2 divided by 10.
Okay, yeah, that makes sense. Okay, right, yeah, I'll use that for the next time.
It's better than 0.0693 because 0.0693 is approximation anyway. Okay, good job.
Yeah. Okay.
So thank that's Karina, right? So I think the next one, David. Then after David, Yaprak. So those from 6, then we go from 7.
So I made this problem where a person throws a baseball from outfield to home plate, and it decelerates proportional to the difference between 125 miles per hour or 183 feet per second and its velocity. It takes 3.4 seconds to pass third base at 90 miles per hour or 132 feet per second and reaches home plate at 87 miles per hour or 128 feet per second. And the question is, how long does it take to reach home plate if the velocity leaving the player's hand was around 94 miles per hour or 138 feet per second? So you can set up the equation as dv dt, because that equals acceleration, equals absolute value of 183 minus v, the velocity, times a constant k, because it's proportional. And then I separate the variables. I divide by 183 minus v, and then I multiply by both sides by dt. I think this is a mistake. It should be 183, not 125 in the denominator.
I was thinking, where does 125 come from?
Yeah, I'm sorry about that. Yeah, I kept trying to find better numbers, so I kept erasing stuff. And so you can well, this after you differentiate. I'm sorry, I kind of skipped the steps here. It's going to give you negative ln 183 minus v equals kt, because you just tag on a constant at the end over there, where c is just the difference of the two constants you get on either side. And then after that, we raise everything as an exponent of e, and then we have 183 minus v equals e to the negative kt minus c. I let e to the negative c equals c1, and then the new formula is 183 minus v equals c1 times e to the negative kt. And so we can get the formula for v of t by just subtracting both sides by 183 and then multiplying by -1 to get rid of the negative in front of the v. And so we have v of t equals 183 minus c1 e to the negative kt. And so we have to go about finding our constants. First, we're going to be finding our c constant, because conveniently we can take it at time 0. We can ascribe the velocity of 138 feet per second while making t equal 0. And so we plug those in, and e to the 0 becomes a 1, and so you just have c1 138 equals 183 minus c1. You subtract and you divide by -1, and you get 45. And so you can plug that into the equation. Now we have v of t equals 183 minus 45 e to the negative kt. And then we can take our second case of when the ball passes third base at 3.4 seconds and at 132 feet per second, and we could plug those numbers in. We get a value of ln of 51 divided by 45, equaling our constant, negative of a constant times 3.4 divided by the negative, and then we get this decimal here. There was no real nice way to put it, I suppose, so I just left it as a decimal as negative 0.0368. I plug that in, and then I take in the last bit of data that it reaches home plate at 128 feet per second. This allows me to plug that in and then solve for time. I plug it in, I subtract 128 minus 183, and then I divide by the -45. Just take the natural log on both sides, so that gets rid of the e, and then we end up with t equaling 5.45 seconds, and that's my final answer.
Okay, all right, thank you. So I think Yaprak, right? Also from 6.
Yeah.
Okay.
Okay. So my question is, consider crossbow bolt shot straight upward from the ground, y equals 0, at time t equals 0, with initial velocity v0 equals 49 m/s. Use g equals 9.8 m/s squared and nu equals 0.0011. When does the bolt reach its maximum height? So
hold on 1 second. Let me understand your notation. So V0 is 49, I guess is meters per second?
Yeah, it's meters per second.
Okay, then G, what is G? 9.8 meters per second square?
Yes.
So that's what?
So that's the, G, like G-force.
Oh, okay. Okay, G-force. So
it's like the physics thing. Yeah.
What's P? A rho
P
or
is,
P?
Yeah, it's rho.
A rho.
Yeah, it's rho.
It's a constant of 0.0011.
Yeah, I found it online though. So
it's a constant.
Yeah, it's a constant. And it was given.
Okay, I guess those are physical terms.
Yeah,
Physics.
I think, yeah.
Okay.
But like it deals with upward motion, so we can like use this differential equation. So that's why I picked this question.
Okay, great.
So like I said, it deals with air resistance and we have upward motion. So we can use the equation dv over dt equals minus g minus nu v squared. So I factor out minus g, and then I got minus g times 1 minus nu over g v squared. Then I rearrange the equation. So I multiply both sides by this. And then I got this equation. And then I took the integral of both sides. So the right side is easy. It's just minus gt plus c squared, c sub 2 constant. And then the left side is the derivative of arctan. So we have, when we take the integral of the left side, we get radical g over p arctan of velocity times radical nu over g plus c1. And then I plug it in the given values. So our g was 9.8 and our nu was 0.0011. And then here I simplify it and I got this constant. And the same thing here, I also simplified this. So I multiplied radical nu over g times velocity, which was 49. Then I rearranged the equation again here. Like I combined the constants. And then later on, I find the constant, which was 0.47885. And then what I did, okay, and then to get rid of from the arctan, I took.
No, I think you use some initial values.
Yeah, I used them.
Yeah, like you use V0. Right, V0
yeah, I use V0 here. Yeah. And then like this equals to, this, like you switch this side with this side. That's what I did here. And then I got the velocity function. And then the question was asking when will the bolt will reach its maximum height. So we know that when velocity is equal to 0, you'll get the time that it reached, you'll get the maximum height. So I let v equal to 0, and then I solved for t, which was 4.61 seconds.
Okay, all right. Okay, thank you.
Welcome.
Okay, I think that's all right. That's all from 6. The rest of us from 7. Okay, let's see who's, oops, hold on a second. Okay, Su Xian has 7.1. Let's go from 1. So 1, then Anqi presented 3, Liz 4. So Christian is 4 also. So Christian and Liz, make sure you have different questions. Ryan is 7. Which number? Oh, Ryan has his own number of question. That's great. Okay, Su Xian. Yes, your work is up. No, I think your Mac has the same problem as another night. Yeah, you're muffling on the other side. I cannot figure out what you're saying. Your sound disappeared. Okay, maybe Su Xian, you fix it. Okay, so let's try 4. Christian, you put up 4 first, so 3.74.
I'm going to do a substitution because Liz has the same question.
What do you mean you want to do substitution?
It's sort of like Ryan. It's my question, but it's on the lines of the question that's in the section.
Oh, okay. So it's not the question. It's not the same question as Liz. So Liz's question is truly 7.4.
Yes.
Your question, you made up yourself. Okay. So Su Xian, what's up?
Device stats. Can you hear me now?
Oh, yes. We
Okay.
can hear you now. Go ahead.
Can I start now?
Yes, go ahead.
Okay. I'm so sorry. So,
That's
okay. The question I chose for the 7.1. The question is verify that y1 equal like e power x and y2 is x times e power x are solution of the y double pi minus 2y pi plus y equals 0 that equation. And then show the y1 and y2 are linearly independent and find the particular solution to the differential equation and y such that the y of like a 0, that's the initial value equal 2, and y pi of 0, that initial value equal 5. So there are like 3 like question. First of all, I need to verify y1 and y2 are solution of the function. So that's very easy. If you want to verify, it's like a solution for the function, I suppose, and plug out all the things into that equation is make them equal. So let me start with the y1. Y1 is like a e power x, and then the y1 pi is equal e power x, and then y second pi is equal e power x. So we plug in to the equation like a y double pi minus 2y pi plus y equals 0 is like, take a look, is e over pi minus 2e power x plus e power x equal 2ex minus 2ex equals 0. So y1 is the solution for this function. And y2, I use the same thing. Y2 is equal x times e power x. Y2 first pi is e over x plus e power x times x. I use I use a product rule to do this one. So the y second pi is equal e power x plus e power x plus e power x times x. Also, this one I use the product rule too, and get the solution is 2e over, no, power x plus e power x times x. I plug in into the equation y2 like a double pi minus 2y2 pi plus y2 equal x times e power x plus 2e power x minus 2 times e power x times x plus e power x plus e power x times x. So finally, the solution is 0. So the y2 is like a solution for the function. So y1 and y2 are the solution of this function. The number one I did. The second one, okay, I need to like find out y1 and y2 are linear independence. So for that person, I don't know who is this. I didn't check that. It's wrong key of f and g. That's like a two function, like fit this w f x g equal this matrix f g f pi and g pi equal f g pi minus g f. If I let like a y1 equal f, g equal y, so I got like a w is like a e over x, and then x times ex. So x like a question one I have like y1 is e power x, y2 is x times e power x, and then a y1 first pi is e over x, and then a y2 like a first pi is e over, no, power x plus e power x times x. So I plug in into a matrix, and then I get is e over, no, e power x times e power x plus e power x times x minus e power x times e power x. So I get the answer is e power 2x. So this is not 0, because when the x is 0, so e 0 is 1. So this is 1 is not 0. So as like a theorem is y1 and y2 are two solutions of this homogeneous like a second order linear equation, because and then a y second pi minus 2y pi plus y equals 0. This is like a right hand side is 0. That's a homogeneous like equation. So fit 1, and then this one is for this one is 0, and it's not equal 1. So y1 and y2 are the linear independence. That's by the theorem. So we solve like a second question, and then third one, we need to find a particular solution for the differential equation y. So there like we know that y1 and y2 is solution for this homogeneous like equation, and then they are like a linear independence. So that's why it fit this equation. C1 times y1 plus C2 times y2 equal y. So we have the y of like a 0 initial equal 2. We plug in this function. So 2 equals C1 times e power x plus C2 times x times e power x. So we know C1 times because, and then this is 0. So that's why x is 0. So E0 is 1. So plus C2 times x is 0. So that's why I don't need to count this one. The second thing is like 0. So C1 is equal to. So we get like a C1, but we suppose need to find a C2. So we know that like y first pi of like a 0, the initial equal phi. So we plug in over there phi equal like C1 times EX plus C2 times and then the E power x times E power x times x. Like phi equal to this one x is 0, so the first one is 0. Plus C2, the first one is E0 is 1. And then here has x is 0. So C2 is like equal 3. So we plug in C1 and C2. We got the solution like a y equal phi E power x plus 3 E power x times x. That's my solution for question 1.
Question, the third part of it. Thank you. Yeah, very detailed. Yeah, you can lower your hand now. Otherwise, they always show.
Oh, sorry.
That's okay.
Thank you.
Okay, great. Thank you. Israel wants to present something similar to 6.3. Go ahead.
Oh, yeah, sorry. I was moving some things around. Do I have presentation? I don't think I do.
Oh, yeah. I have to make a presentation first. Sorry about that. Yes, you are now.
Okay. Let's see. I should do it. Okay, is everything seen?
Yeah.
Okay. So I chose 6.3 modified, and essentially what I did is I kept the the acceleration equation, and all I did was modify v of 0, and as well as making it so we have where t equals 15, v of 15 is 30 feet per second. So
I'm sorry, what's your v of 0? I cannot see it. V of
70 feet per second.
Oh, okay.
Yeah. So essentially it's just how I think Ryan presented this too as well, like a similar thing. Yeah, so we have our general equation, which is v of t is equal to negative p of t plus c3, which is to the negative power, to negative 1 power. That's what I put it as on there. So then, as we do, I solved for t at 0, which gave me c of 3 as 1 over 70.
Hold on a second. Let me try to understand you. Okay, so you are saying, so you made your own 2 initial values, right? V of 0 equals 70, V of 15 equals 30, right?
Yeah.
Then what's after V of 0? After V of 0, you have integrate 1 over V squared dV equals to into negative P, what is this, dP, dt?
It should be 1 over v is equal to negative p of t plus c of 3, and then I'm basically v.
No, that's 1 of v squared, right? Right, you skip some steps. That's right.
Yes.
I just understand you. Right, just can you explain what are you doing here?
Yeah, so I just solved for the general equation for 6.3.
For v,
then,
right?
Yeah.
You're trying to find the velocity function. Yeah.
On the velocity function. That's the same as the unmodified version. And
right.
Now
on the same line of v of 0.
Yeah.
So you have integration. Basically, you separate your variables, then you integrate both sides. That's what you did?
v of 0. No, for v of 0, I solved for when v of 0 is equal to 70. So then just plug in.
That's some condition you made up. That's the initial condition you made up, right?
Yeah, yes.
Yeah. So after that, my question is after that you have integration 1 over v squared dv equals to integration negative pt.
Oh yeah, sorry.
Negative
Yeah. Okay, now I see where. Okay, yeah. Yeah.
So
Apologies. No, I put this too close to it.
Crucial. This is a very
Yeah.
crucial step. You know, the rest of the question is just arithmetic. You did something here from the first line to the second line. That's the key point.
Oh no, now I understand. Yes, apologies. Yeah, it's because I put it too close. This note I meant to erase the v of 0 and v of 15. I meant to state that, but I accidentally forgot to make up the question. But essentially, it's just the integration is separated from v of 0 from my made up values basically. I basically solved d of v over d of t equals negative p v squared. I did that normally. How would it be done on the unmodified version? So I then solved for d of t.
Right, you started with a given equation, dv over dt equals negative pv squared, right? So what's your next step?
Then what I basically did is that I divided both sides by v squared, moving over the v squared to the left. I then moved over the d of t to the right, so then I can integrate them.
Okay, so you separate the variables basically. Okay.
Yes.
Right. Then you integrate on both sides. Okay. Point. Yeah.
So then I solve for v of t. I then plug in my values for 0 to solve for C3, which gives me 1 over 70. That's that second part. And so then I would have to solve for P. So for P, I plugged in my T value, which was 15 for this case, as I made up. And I equaled that to 30, because that's also the value I made up. So to do that, this one I did skip a lot of stuff. Okay. Oh yeah. So essentially what I didn't illustrate this, but essentially what I did is I once again flipped over the 30 to make it 1 over 30. So then I could just have negative p times 15 plus 1 over 70 as no longer being 1 over negative p of 15 plus 1 over 70. So then I could subtract 1 over 30 minus 1 over 70, which would then give me 4 over 210. I then...
Really? Hold on a second. Yeah. Yeah, because you skip so many stuff.
Yeah. Yeah. And then after I got 4 over 210, I then multiplied the left-hand side by 15, which gave me 60 over 210, which is equal to 1 over negative p. I then solved for p, which was just negative 7 over 2. I simplified that, which makes my velocity equation.
Okay, yeah, go ahead.
Yeah, which makes a velocity equation v of t equal to 7 over 2 times t plus 1 over 70, and that's all over 1. That's all under 1. I just put in negative to the power of negative 1 just to simplify it for my sake.
Positive 7 over 2?
Yes, it should be positive. Because if this is negative over p, it should come out as positive.
I think it should be negative. Because under here you have negative p times 15, right?
Yeah.
So you have negative, then the other side you have 1 over 30 minus 1 over 70, you got 4 over 210. Isn't it should be negative?
No, yeah, p equals negative 7 over 2, but because the initial equation that I'm plugging it back into is negative p, it would mean it become a positive.
Oh, okay.
Yeah.
I see.
Yeah, I thought that too, and then I had to go back and check.
Okay, I have to tell you, this is a poor presentation, okay? Because you are asking me, because I have to figure out so many things. All right,
Yeah.
so hopefully next time you do better, okay?
Mhm.
All right, now
Okay.
let's back to, I'm lost. Okay, I think it's Liz, right? Or Christian? Liz, 4, right?
Yes,
Okay.
but I don't know if Christian wanna go first because it was supposed to go before me.
Who? Christian?
Yes.
Christian's saying he made up a question similar to 4. So maybe you can go first.
Okay.
Yeah. Then after Liz, Christian, you get yourself ready, okay? After Liz, we have to go a little bit faster. Almost 9. Then anybody present 5? Excuse me. Oh, Jun Yi has 5. Then lastly, so we have 6. Okay, I think we'll leave Ryan for the last. Ryan made up a question himself too. Okay, Liz, your work is up. Go ahead.
Okay, I wanna present question 4 from homework 7. This is about linear second order equation with constant coefficient. So they are usually of the form a y second plus b y prime plus c y equals to 0, where a, b, and c are real numbers. So to solve this type of equation, we're gonna try to put y and equals to e exponent or x. So if y is or exponent e exponent or x, sorry. So y prime is, which is the derivative of y, would be or e exponent or x, and the second derivative will be r square e exponent or x. So that we have those 3 values, we're gonna go and substitute that. We're gonna replace the first derivative. We don't have the first derivative in this particular one, but we're gonna go ahead and replace the second derivative and y by the new value that we have now. So y second will become r square e
Hold on a
exponent.
second, Liz.
Yes.
Everyone, well, this is talking to everyone also to Shuxian before, because I didn't stop her. We can read the second power of y as y double prime. Okay, the first derivative we could read as y prime. So y prime, first derivative. Second derivative we could call double y what? Y double prime. Okay. What the second derivative of y?
Okay, so
Okay.
I should say second derivative of y instead of.
Yeah, you could call y double prime or the second derivative of y.
Okay. So we replace the second derivative of y by r square e exponent or x minus 4 e exponent or x, which where e exponent or x is just the new value for y. So next we factorize by e exponent or x. So it's e exponent or x times r square minus 4 equals to 0. We know that e exponent or x cannot be equals to 0, so it must be r square minus 4 equals to 0. So here I use this formula, which is a square minus b square. It's just a minus b times a plus b. So it's r minus 2 times r plus 2 equals to 0. I did each factor separately. So r minus 2 equals 0, or is 2. R plus 2 equals to 0, or is minus 2. So y1 is equals to c1 e exponent minus 2x, and y2 is equals to c2 e exponent 2x. Those are like two solution, and then like the general solution will be y equals to c1 e exponent minus 2x plus c2 e exponent 2x.
So it's looking for the general solution, right?
Yes.
Okay. Anyone has any questions? All right. Basically, those students are teaching us the new material today. Let's see if there's any question. Okay, Moise is going to 7.7. Okay, thank you, Liz. So that's 4. Christian, are you ready? Lecture 6. Lecture 6, did we finish? Lecture 6, I started, right? I didn't finish. We're going to finish 6 and starting 7. Yeah. Hopefully we have time. Hopefully we have that time. Okay, that's Christian.
You can see it?
Yes.
Great. Okay. So this question is on the lines of what Liz just showed, but it's different in the fact that we have a discriminant that is less than 0 when we're solving it. So right now I'm supposed to find the general solution of this differential equation, the second order differential equation, and it's rather simple. You have to just put the coefficients in the form of a quadratic. Your 8 is going to be next to r squared, that coefficient, and then your -1 is going to be your r coefficient, and then your 2 is going to be your constant, and then you could just use the quadratic formula to get your answer. When I used the quadratic formula in this circumstance, I got that my discriminant was less than 0. So
hold on. Hold your horses, Christian here. So you're saying you let y prime to be r, right? So if
yes.
y prime is r, the second derivative is r squared?
The second
It's
derivative,
only for some special cases.
the coefficient of the second derivative, it should be r squared. I mean, it should be a in front of r squared.
No. So my question is, so your y double prime is the second derivative of y, right?
Yes.
Okay, and the y prime is the first derivative of y.
Yes.
Okay, so you want to use r to representing y prime, first derivative, right?
Mm-hmm. Okay.
Okay, oh, you have 2y here. So 2y, hold on a second, let me understand your notation. 2y becomes 2. So your r is not y prime. Your r is y prime divided by y.
Okay. I have an example. Well, I have like a notation. I can show you it right now. Of how I got it. I'll just pull it up. It's gonna be simple, real quick. Just
Okay.
have the PDF. I'm gonna switch it. Okay. I knew that it would probably need more clarification.
Yeah, because I just want to. I need to understand your r. Your r and r square. Yeah.
So concept that I use, wait, pull up the proper one. Okay, go there, downloads.
Jun is saying, he said e to the rx equals y. Oh, y equals to e to the rx. Oh, that may make sense. Because I didn't see.
Equal to e to the rx. Yes, it's equal to e to the rx.
Oh, that makes sense. Okay. Then if you divide by e to the rx. Okay, let's go back to your notes.
Yes.
Yeah. Right, that's for special case. I was thinking if we don't know why, you know, we cannot just do that. But if we know why, that's okay. So, right, you didn't write down your why.
Yeah, y is equal, I have it right here. Y is equal to e to the rx, y prime is equal to r e to the rx, and then y double prime is equal to r. Huh?
I don't see them. Where are they?
Oh, I'm gonna pull. Okay, I want to pull that part up right now. I wasn't totally sure.
You should write with your equation here, right?
Okay, I have it right here. I'm showing you. But this was in a different circumstance. I had to switch up my question.
I see. Jun saved you. Jun, we heard you were saying y equals e to the rx.
Okay, right here. This is what I was doing. This is a different question, but right here to the right was what I was doing.
Oh, okay. So your y equals to e to the rx, your y prime equals to r e to the rx, y double prime equals to r squared e to the rx. Now your substitution makes sense. Now you can use r to represent your y prime, use the r squared to represent your double prime. All right. Okay. Now I'm clear. Go ahead. You can go back.
Okay. I'll just stop sharing that. Okay, and yeah, homework 7. Okay, so yeah. Now going back to that, knowing that y is equal to e to the rx.
Okay. I apologize because you said your question is based on the question 4. Yeah, I just forgot about that part. Yeah. Okay.
Okay. Yeah. So yeah, sorry. I should have included it because like I felt like the question was so easy that you didn't really like need that information, but to someone who doesn't know, I understand that I should have showed it.
Well, you could write down something like this related to 7.4, or just simply define your why. It would be so much easier.
Yeah, I'll definitely be more sure to be clear.
Thank you.
So so y equals to e to the rx. In doing that, I could create this quadratic right here, which is 8r squared minus r plus 2 is equal to 0. The discriminant is going to be, when we're using the quadratic formula, it's going to be less than 0. So we're going to have an imaginary number popping out. Well, really complex if we take into account the 1 over 16. So it's a complex number. So the discriminant is negative 63. It's just the square root of 63 times the square root of negative 1. Negative 1, the square root of negative 1 is defined by I. So this would be the output 1 over 16 plus or minus the square root of 63 over 16 times I. And in having this as our out, we're going to say define R1 as the positive. So define R1 as 16 plus 3 times the square root of 7 over 16i, and then the R2 is just going to be 16 minus that same number, and then we're going to put it into the general form of e to the power of alpha x, it multiplied by our first constant cosine beta x plus our second constant multiplied by sine beta x. So we want to get our alpha and our beta out of our R1, which is a positive, right? The same as, because we want to find our beta and our alpha, but we don't want to find our negative beta, so we're going to use R1. So we're going to take out 1 over 16, put it into this general form, and then we have our general solution. And we do the same thing with 3 times the square root of 7 over 16 and place it inside of this general solution. It's not that difficult to remember. So yeah.
Great. Very smart. Very smart approach. You figure out this yourself?
I actually got help from the organic chemistry tutor.
Okay.
So yeah.
All right. Thank you for showing us. Okay, let's see. So Junyi, your turn now, 7.5. Then Moises, 7.7. Anybody present 7.6?
Sorry, give me 1 second. I have to share. 7.5. So this question is kind of similar to 7.4, actually. So it just find the general equation. So by the given differential equations. So it has like y double prime plus y prime minus 2y is equal to 0. So I do the substitution as they did before. So let y equal to the e to the rx, and then take the first derivative and the second derivative, which is equal to the y prime equal to re to the rx, and y double prime is equal to r squared times e to the rx. So I plugged into the equations, so it becomes r squared e to the rx plus r times e to the rx minus 2e rx, 2e to the rx, sorry, equals to 0. And then factor out a common variable, so e to the rx times, so it's times the r squared plus r minus 2 equals to 0. So I can factor out also the r squared plus r minus 2 equal to the r plus 2 times the r minus 1 equal to 0. So I can get r is equal to -2 and r is equal to 1. So since like two numbers are not equal, so they're independent, so we can use the general equation, which is y equal to c1 y1 plus t2 y2. So I plug the r back into the y equation, which is y1 is equal to e to the -2x, y2 equal to e to the x, like 1 times x, so which is e to the x. So the equation could be y equal to the c1 times e to the -2x plus c2 times e to the x.
Okay, so Christian, even your solution is different, interesting, but I still prefer this way, okay? I think this way is direct, more direct. All right, thank you, Julie. Anybody present 6? No, right? So I think it's Moises' turn. Question 7. Then lastly, we go with Brian.
Can you make me a presenter?
Oh, I did not? Oh, sorry. Here. So for 7, we're only missing 6, right? No one presenting 6. Okay, you're presenter now.
Hello, can you see it?
Yeah.
Okay. So, for number 7, it was almost the same as the last two, but so yeah, the start is we just set y equals to e to the rx, and so because y is equal to e to the rx, that means that the first derivative is r times e to the rx, and y double prime is r squared times e to the rx. And so we substitute back to the original equation. So we have 4 times r squared e to the r squared minus 12r times e to the r squared plus 9 times e to the r squared equals to 0. And we factor out e to the r x to solve the square. And we know that e to the r x cannot equal to 0 no matter what r or x is. And so we are left with just r equaling to r over 2. So there's no c2 or e to the r2x. It's just one solution.
Right, because it's squared.
Yeah, because it's squared, so there's no need for a second one.
Yeah. All right. Okay, and Ryan, your turn.
So I basically did a question similar to 7 and kind of 8 and 9, and that's finding the particular solution to this differential equation when y0 is equal to 15 and y prime at 0 is 25. Just basically chose random numbers. However, if you make a parabola out of this, that's kind of what Christian was mentioning. If you make a parabola 3x squared minus 17x plus 18, it has two roots on the x-axis. If it doesn't have roots, then you get sine and cosine in your answer, and then you get the imaginary numbers. That's where they're from.
Okay, so your y is still the same y, e to the r.
Yes. I'm just saying the numbers, basically, if the numbers come out to form a parabola that doesn't have an x-intercept, that's where imaginary numbers come from. That's why some answers come out with sine and cosine. So basically, for differential equations like this, we're looking for something. With cyclic differential or cyclic derivatives. So that's e to the x or sine x or cosine x. But if you look, we have positive, negative, positive, and as you know, with sine and cosine, it's every 2 that swaps the sign, not every 1. So it can't be sine or cosine. So as we already know, it's been presented a bunch, it's e to the x. And in particular, it's e to the rx, where r is a constant. And so when we derive that, we basically pull the r out and we still have the original function. And same thing, when we derive that again, we get r squared. And so we plug that into the differential equation. And of course, we can basically pull out all the e to the rx's. And since we're not really solving for that, we can just get rid of it and use this part. And so we basically have a parabola just in terms of r, not x. And so quadratic equation, boom, there's your two roots, plus and minus. Since they are not the same, we have to do a constant times e to 1 root times x, plus a constant times e again to the power of the other root times x, and that's our general solution. To work through the particular solution, we basically use y of 0, and the e's they become 1, right? So that basically goes away, and we have whatever y at 0 is equals c1 plus c2, and we take the derivative. So r comes out, but e again cancels out. And so we have 25, that's my y prime at 0, equals, again, the two roots times the two constants. We have a system of equations we can plug in and solve. In this case, because I chose numbers with very complicated roots for that parabola, there's a lot of algebra involved. And as you can see, the number is not pretty. So that's one of them. And then when you plug that back in, you basically, what's that called? You get the negative of the radical on the top, but everything else stays the same. But basically, yeah, we plug that back in. There's our constants. There's our particular solution. If you check that in a calculator, the calculator will explode. Especially when it tries to compute 0. After 6, it goes crazy, but it's equal to 0. So there we go.
Okay, I like this. Especially, I like you keep this square root of a number. You do not approximate. Because in college, until we work with life applications, we want to keep it pure. We want to keep, irrational numbers. That's just irrational numbers, like ln some number, square root of some number. That's fine. We want to keep them as it is, exact. Okay, C1, C2, C1 You mean this C2, right? Oh, C1 plus C2.
Yeah, this is C2,
Okay.
this is C1, so we plug
Okay,
this
we
in
call
there
them,
and this in here.
look at, it's like a A plus B, A minus B, right? If C2 is A plus B,
Yes.
C1 is A minus B. We call them conjugates.
There you go. Yeah, I forgot the word.
All right, great. Thank you.
Thank you.
I think Ryan's the last one, right? Anyone else I missed? Did I miss anyone? Okay, now let's go to 6. So hopefully we have enough time to finish 6 and go to 7. Oh, that's not what I want. I want to go here. So I want to go to, although this is day 7, I need to go to day 6. Right. Let's see. How far have we gone? Did we do this example? I forgot, but this should be an easy example, right? Some of our classmates showed enough questions about this model. Yeah. What do? We separate variables and we integrate both sides simultaneously. If we have initial value, right, in that case, we get a function of velocity. Give us, well, this is just a general solution, carry a constant, give some initial values, we can get a specific velocity function. Then we can use that velocity function to find other values, especially this constant, rho or p, rho, I guess. This is approximation, but this can be simplified. ln 1/8, just negative ln 8. Negative times negative positive. You could keep it as ln 8 divided by 20. Actually, what's ln 8? ln 8 is a 3 ln 2, right? You could keep as a 3/20 ln 2. It's fine. It's just an irrational number. Then we can integrate that, get a displacement function, use some initial values to get a specific displacement function. If we want to find the maximum, especially like this one, see how far will the car coast before it stops? Right, how far? So we don't know the time. So what do? We take a limit. We want to reach its maximum. We take a limit, we let time run to infinity. So this is saying at most it can go 846 feet to its stop. If anyone has any questions, feel free to stop me at any time. All right, because some of this material I feel our classmates have presented enough. With resistance, Newton's second law, maybe you're physics majored, you can go deeper with this. Okay, so that's one of the students. That's why I asked her, what is a G? Right, so she's using this differential equations. G and rho and V square appeared. Velocity square appeared. Oops. Let's go over this one. Special physics majored. All right. So when resistance is proportional to the square of the velocity, okay, just one of the differential equations. Assume the air or any resistance is proportional to a square of the velocity. So the force of resistance is plus minus k v squared. Or in this case, because we carry plus minus, so k we define as a positive number. The choice of sign has to do with the direction of motion. If we take the upward direction as a positive, then So this less than 0 will be positive motion. If we take the upward direction as positive. Oh, then the resistance, right? When the resistance is less than 0 will be positive motion. So resistance force is always opposite of the velocity because it's resistance. So we can write as the force of resistance is as a negative kV with absolute value of V, or so Newton's second law of motion gives us this. Or this. Or, yeah. So upward motion. Suppose a projectile is launched upward from an initial position y naught with an initial velocity v naught, which is positive. Then, so we have this, because the initial velocity is positive. So get this equation. And if we factor out negative g, we can rewrite this as this. Then we can separate variables, right? Separate variables. Then we integrate at both sides. If we use u to substitute the square root of rho over gv, and then we can get, so that's what Jun-Yi, I think, showed in her homework. Because when we integrate this, the arctangent, right? Arctangent, what we need to factor out this. Well, we need to make this a square term. So this rho over g will be square root of rho over g squared. Then we get an arctangent of this. V square root of rho over g. Then the rest just, right. So this will on the exam, all right, because some of us won't be able to remember the integration of arctangent. Integration of arctangent is 1 over 1 plus something squared. So the rest is just solve this equation, simplify this equation. So in the end, we get arctangent of this such angle equals to this. So we rewrite as a tangent, right? Arctangent we rewrite as a tangent. So that becomes a tangent of this equals to this. Then we solve for v divided by square root of rho over g on both sides. So we have our velocity function as such, square root of g over rho tangent of this negative square root of rho g then times t plus a constant, general solution. Then we use this initial velocity. So arctangent initial velocity is 1 times 0. We'll just plug in times 0. Just have this. Then the constant. So we can solve for the constant. The constant is this. Depends on the initial velocity. To find a position function, we integrate. Right? We integrate this. How do we integrate that? Tangent, well, let's use u to substitute for this. So tangent u is sine over cosine. Right? Then we could use another variable to substitute for cosine, 1 over cosine. That's ln cosine. Right? Sine u du. Just we could use maybe w, right? See, w equals to cosine u. So 1 over cosine u integrate the ln cosine u, of course, with absolute value. Then dw is just sine u du. So integration just this. And then so y of t is this, and then we want to okay, what did we do? Oh, okay, we got rid of the tangent, right? Because we have integration. We're trying to integrate this tangent. So in the end, what do we get? We integrate. After integration, we get such ln with cosine stuff. Okay, downward motion is similar. I want to skip it. If you're physics majored, maybe you want to go through the details. Okay. Let's just skip this. This is, well, let's see this example. Assume resistance is proportional to the square of the velocity. How far does a car from the early example go in the first minute? Same thing, right? So by now, we're very familiar with this now. Separate variables, solve for velocity, use the initial value, get a specific velocity function, then integrate, get a displacement function. The first minute. I guess the original one is per second. That's why it becomes a 60. First minute becomes a 60. Yes, Gregory.
Hi, Professor. Can you hear me?
Yes, I can hear you.
Okay. I have a question. Did you mention stuff was from physics? Stuff.
Oh, yes. These ones.
Can I see it again?
Can you see the screen?
Uh-huh.
Talking about the ear resistance and other resistance, talking about the upward motion, downward motion.
Okay.
Yeah, you're a physics major, I guess.
No, I'm not a physics major. Can you explain those terms to me, please?
Oh, I don't want to explain them because you're not physics major. That's why I intentionally want to skip those.
So,
Don't
okay.
worry about it. Don't worry about it. Yeah.
Okay.
Don't worry about it. It won't be on your exam.
No problem.
Okay. I'm a little bit behind my schedule.
Wait, I have a question as well. Can you go up for a second, like to the first example?
Sure.
Yeah, like somewhere. Yeah, can you? Yeah, like here, a little bit down. Just yeah, right here. You see where it says v equals to e to the power of pt minus c2? Like in the middle?
V equals to, oh, this one?
Yeah. And then
Yeah.
in the next one you have a c3 because that's what I did on my example, and you said that c2 doesn't equal to c3. So why is it there?
Yeah, can you tell me why is it C3?
I don't know, so I'm asking you.
Okay,
Like,
if
I
you
want more
split this,
explanation.
well, first C3 is just a just a variable, right?
Yeah, that's what I said as well.
This,
yes.
Yeah, this is a nice way to write with the e term. Because if you write e raised by negative pt multiplied by e to the negative c2, if you write e, you have this e to the negative pt minus c2, it's kind of annoying because you have two exponents, right?
Right.
You want to split it into e to the negative pt multiplied by e to the negative c2, right?
Right.
Now you just use c3 to define your e to the power negative c2.
Okay, but you said that c2 doesn't equal to c3 when I did my example.
They do not equal to each other.
Sorry, could you say it again?
Okay, all right. Let's go to whiteboard. If you have a e to the power, can you tell me what does this mean?
Like, what do you mean? What does it mean?
Yeah.
Oh, you're gonna finish.
Yeah. What does this mean to you? What does mean e carries 2 power?
Well, it's. Oh, you're finishing.
That means this, right?
Right. It's the same.
Right. So now I don't want to carry e to the negative c2 with me all the time.
Okay.
So I'm gonna name this c3. Or maybe just c, not even c3, just a constant c. So that's why this is gone. So I can carry c3 with me. Looks much neater.
Okay, yeah, that makes sense.
Okay.
Thanks.
You're welcome.
Thanks.
You're welcome. Okay, let's see. Okay, I think this one we have showed enough, right? Right. Okay, let's go into 7. Okay, 7. I have about half hour. All right. Second order linear differential equations. There's some terms. Well, let's go step by step. A second order linear differential equation has this form. We see y prime or multiplied by a certain function, y double prime, second derivatives, then y prime by a function, and the y by a function. And of course, and this one can be 0, this one can be 0, or this one can be 0, this one can be 0, or this one can be 0, but just not this y double prime. Similar to quadratic functions. Okay, quadratic functions, the second power, the leading term of the second power cannot be 0. Because if it's 0, it just becomes a first order differential equation. All right. So first thing important, those two cannot be 0 to make second order. Okay. But this one can be 0. If this one is 0, and we see the equation is homogeneous and very dear to our eye. Remember before we have such thing, right? We have a function times y double prime. We call, I forgot what do we call P, maybe Q. Did we call PQ or something? But in any case, we see this double prime, this one, then this, then equals 0, or maybe sometimes this on the other side, right? How do we do it? Remember, we use another variable to substitute for the second derivative, right? Then we use another variable to substitute for the first derivative. Then this just becomes the second order of this becomes the first order of a new variable, right? That's how we solve. So if this is 0, so we know how to solve the differential equations, right? Let's say this are examples, right? If this is this equals cosine x, not 0. So this is non-homogeneous. And this also, but this one equals 0, right, is a homogeneous equation. So this is saying if we have this and well, this is not 0, then we can divide the equation by this. So we can get this. We can get y double prime times b over a, right? Y prime and c over a y equals f over a. Well, here just use another variable to substitute the fraction, the quotient. So that's why we call associated homogeneous equation. So if y1, y2 are solutions to a homogeneous equation, then c1, y1 plus c2, y2 for any real numbers, c1, c2 to be. If y1, y2 are solutions to this second order, homogeneous second order, associated, right? Why is it called associated? Because we just divide both sides by this. We just have y double prime by itself. We just give another name. If y1, y2 is a solution to this, then we could, so this, if we substitute y into y1, we get that equal to 0, and substitute y2, we get that one equal to 0 too. So we can plug in c1 y1 plus c2 y2, right? In that case, we can prove that equals to 0 also. Okay, so this, if you want to do a little bit of arithmetical calculation, you can go through this yourself. Right? So this is the important point. If y1, y2 are solutions to the second order differential equation, then c1, y1 plus c2, y2 is a general solution. Okay, c1, c2, just some numbers. Okay, we have a theorem, existence and uniqueness. Suppose PQF, remember what's PQF from the beginning? Here we have this, right? A is the scalar function before y double prime. B is a scalar function before y prime. C is a scalar function before y. And F just functions, the rest of the functions are on the other side. And then we use P to divide B divided by A. We use Q to substitute C divided by A. We use a little f to represent capital letter F divided by A. So suppose P, Q, F are continuous on the open interval I. So this is to be mathematically correct or to be mathematically safe. Containing the point A. Then given any two numbers, B0, B1, the equation y double prime times P y prime Q y equals fx has a unique solution on the interval, satisfies y of A equals B0, y prime of A equals B1. All right, so this is uniqueness and existence. The condition is PQF continues on the interval I and containing the point A. So for any two numbers, the equation has a unique solution on the interval which satisfies this. And this. Let's see an example. So we want to verify y1 equals e to the 5x, y2 equals x times e to the 5x are solutions to such equation. Remember, Shu Xian showed present the first homework, right? B, find a unique solution for the initial condition, given those two initial conditions, right? B0, B0. This is our A is 0. So y1 equals to e to the 5x, y1 prime will be 5 times e to the 5x, and y1 double prime will be 5 times 5, 25, e to the 5x. y2 equals x e to the 5x, and y double prime, y primed, y2 prime, product rule, y2 prime will be 5x e to the 5x plus e to the 5x. Y double prime will be, well, e to the 5x is 5 e to the, is this 5 e to the 5x. Right, derivative of this, product rule again, 5x becomes 5 e to the 5x becomes 25 e to the 5x times x plus 5 times e to the 5x. So now adding those two, we'll get a 10 to the e to the 5x plus 25x e to the 5x. So plug in y1, y1 double prime, y1 prime, and y1, we did get a 0. Plug in y2, double prime, y2 prime, and y2, indeed, after calculation, we also get 0. So that proves y1, y2 are solutions. So y1, y2 are indeed solutions to this equation. Okay. Let's see B part. B is saying, given us those two initial conditions, y of 0 equals 3, y prime of 0 equals to 13. So we want to find unique solution for these initial conditions. Remember the theorem. The theorem says y of a equals b naught. Here our a equals 0. Y prime of a equals b1. So b naught in our case is 3. b1 in our case is 13. And a equals to 0. All right, so we use this theorem. So a general solution for y is c1y1 plus c2y2, and write as c1 e to the 5x plus c2x e to the 5x. So use the first condition. So 3 equals to y naught. So c1 e to the 0, c2 times 0 e to the 0. So that's just c1. That means c1 equals to 3. c1 equals 3. So we have 3y1 plus c2y2. Well, now we want to solve for c2. Use second condition. So y prime of 0 equals to 13. Right. So what's y prime? Y prime is such. So plug in c1 and plug in 0 for x. Then what do we get? We get a 5c1 plus c2 equals to 13. And we know c1. c1 equals 3. So plug in 3 for c1, we get c2. c2 equals -2. So a unique solution is this with the condition given. So a unique solution is guaranteed with the initial conditions given. So y equals to 3 e to the 5x minus 2x e to the 5x. Okay, anyone has any questions? Pretty direct, right? All right, let's go to linear independency. So definition for linear independency. So two functions on an open interval I are said to be linearly independent on I. So those are just, for pure mathematics to be mathematically correct, provided neither is a non-zero constant multiple of the other. If two functions are not linearly independent, we see that they are linearly dependent. Okay, if they're not linearly independent, we see they are linearly dependent. So let's see this example. So each above pair of functions is linearly independent on all real numbers. So sine x, cosine x, e to the x, e to the negative x, sine x, x times sine x plus 2, x squared, x, absolute value of x. So those are the pairs. If there's a dependency, that means one can be written in terms of the other, right? We see these ones, we cannot. Let's see an example. So f of x equals to such cosine square x minus sine square x, which is just cosine of 2x, right? You see this? Cos square x, cos square minus sine square of the same angle. This is cos, it's just cos 2x. So this one we can write f of x equals to 3g of x. So the two functions above are not linearly independent. Or to see the two functions are linearly dependent, which means we can write one in terms of the other. Because clearly f of x equals to 3g of x, right? Or g of x equals cosine 2x equals cos square minus sine square, which is 1/3 of f of x. So when two functions are dependent, right, that means we can write one thing, we can use one to represent the other. Linearly independent means there's no way you could use one to represent the other. So the second order of homogeneous equations will always have two linearly independent solutions. Just choose two solutions. y1 of a equals 1, y1 prime of a equals 0. And then y2 of 0 equals y2 of a equals 0, y2 prime of a equals 1. So in fact, if we have two linearly independent solutions, y1, y2 of such second order associated homogeneous equations, then every solution of this equation is of this form, because there's a linearly independency. And so this one we showed before. Let's go back a little bit. Right here, right? You see here says y1 and y2 are solutions to these homogeneous equations. So then c1 y1 plus c2 y2, well, c1 y1, c1 c2 just some real numbers, are solutions too. So this proves that, right? y1 is a solution, y2 is a solution. Then for any c1 c2, c1 y1 plus c2 y2 is also a solution. Liz is asking, what happened when y1 equals y2? Good question. How did we define linear independency? If y1 equals y2, f equals g, that means those two are not linearly independent. They depend on each other if they equal to each other. So this is the example of dependency. Right? Dependency means we can use one to represent the other. So g is 1/3 of f, or f is 3g. If y1 equals y2, or y2 equals y1, the same thing. That's a dependency. Then there's no such c1, c2. Okay, that's a good question. Then this just means the solution. That's just one solution for the equation. This is talking about two solutions linearly independent. If they are linearly independent, then every such form, c1 y1 plus c2 y2 for any c1, for any number of c1, for c1 c2 to be any numbers, is a solution for the equation also. So how we write the general solution? Well, the general solution just one, right? You just have one solution. You just don't have this form. So this is saying if y1, y2 are solutions of this and linearly independent, then every form of this is a solution. So this is general. So every of this form is a solution to the equation, which means this forms a general solution. Let's see an example. Oh, before an example, we define something important called the Wronskian of two functions. Right? So W of f comma g equals to determinant of those four members, four entries. Right? What's the determinant of these four entries? Just f g prime minus f prime g. Just f g prime minus g f prime. What is its purpose? David, what do you mean? Oh, the purpose of Wronskian is to check the independency. It's to check the independency. You will see from the following examples. Okay, to check the independency. Let's see this. Let's first calculate Wronskian to get a little bit idea what is Wronskian. All right. So we have f is e to the x, g is x e to the x. Right. We just put the four members. We find the derivative of f, which is just itself. We find a derivative of g, which is e to the x plus itself. Right. So we put the four members here: f, g, f prime, g prime. Now we calculate the determinant. So e to the x times this minus e to the x times this. Well, this term and this term cancelled. Just left with the e to the x times e to the x, which is e to the 2x. So Wronskian. So notice that if f, g are not linearly dependent, which means are not linearly independent. Because usually we don't use a word, we don't use the term linearly dependent. We say linearly independent or not linearly independent. All right. I don't really usually use linearly dependent. We emphasize on linearly independent. We like linearly independent. So we say not linearly independent. So if f, g are not linearly independent, right? So this is saying one can be represented with other, or that's just a default by scalar. Then the Wronskian equals to 0. Okay, David, that's how we use it. That's how we use Wronskian. You're welcome. Let's see an example. So f is defined as such, e to the r1x. G is defined as e to the r2x. And we want to show those are linearly independent if r1 not equal to r2. If r1 equals to r2, those two functions will be the same. Right? They will be not linearly independent. So we find derivative of f, that will be r1 e to the r1x, derivative of g prime, r2 e to the r2x. So plug in Wronskian. So that's f, that's g, that's f prime, that's g prime, multiply diagonally, right? Determinant of 2 by 2 matrix minus product of those two. Well, the e term is the same, right? The e term is e to the power r1 plus r2x. So we factor out. the E term will never be 0. So we have R1 minus R2, right? If this is 0, that means R1 equals to R2. But we're given R1 not equal to R2. So the Wronskian will never be 0. So because Wronskian is not 0, so those two functions, f and g, are linearly independent. Let's see this one. Oh my goodness, I cannot finish. 2 more minutes. So if y1, y2 are two solutions of the homogeneous second order linear equation of such on an open interval I on which P and Q are continuous, A, if y1, y2 are linearly independent, then Wronskian equals 0 on the open interval. If y1, y2 are linearly independent, then Wronskian not equal to 0 at each point of I. Okay, so this is not linearly independent. Linearly independent. Okay. All right, let's leave this for next time because it's 10 already. Good job, everyone. And for those ones presented today, or especially presented at 7, and for the rest of us, please try to present. All right, you can get credits for presentation. All right, good night. Thank you.
Good night.
Okay, let me stop recording.